right, our last new lesson in Module 7 for algebra is going to be more exponential growth, more exponential functions, but it's going to be growth and decay and kind of the difference between the two. So it basically is what it sounds like. If it's growing, it's going to get bigger, bigger, bigger. And if it's decaying, it's going to get smaller, smaller, smaller. So we're going to look at the definition. It's still y equals a times b to the power of x. A is still the y-intercept. B is still kind of the pattern. The growth factor is what they're wanting us to call it. So b is the growth factor. But in this case, a is greater than 0. Obviously, it's going to be on the y-intercept, bigger than 0. And b is also greater than 1. So if it's going to be something representing growth, this number b is going to be bigger than 1. It's going to be 2 or more. So here's how it looks. I mean, we've already kind of talked about that. The base b is going to be greater than 1, which makes it a growth factor. And this is what it looks like on a graph. I want you to see what it looks like on a graph. If it's exponential growth, the number our graph starts close to the x-axis, and then it hits the y-axis and grows exponentially quickly, grows up. If you think about something that's growing exponentially, like we've had a virus lately, and it's being spread exponentially. So the amount of people who are infected, the graph would look like this as it grows. Something in the stock market that has some exponential growth would be growing just like this. This graph would be exponentially growing. Okay, so then we're going to model with exponential growth. So here's an economics problem. It says since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. So if the trend continues, how much will be spent at restaurants in 2015? So this is a little outdated because obviously it's way past 2015 at this point, but that's okay. We can still do it. They're saying since 2005 to now 2015. So here is it worked out for you so we can kind of make sense of this. X is going to represent the number of years since 2005. So if we're talking about 2015, from 2005 to 2015, it's been 10 years. So we're going to let our x, little exponent up here, be 10. Okay, y is going to be the amount spent at restaurants in billions. So that's actually what we're trying to figure out. So we're going to leave y, but when we get our answer, it's going to be what we're looking for as far as the amount of money in billions spent at restaurants. Okay, a is still the y-intercept. So what that represents is the initial amount spent. So the reason it's 360 is because we're starting at 2005, and they told us that in 2005 about $360 billion was spent. So that's our y-intercept. That's our initial amount. And then b is the growth factor. So that's like the pattern. If it's growing at a rate of 7% each year, this is kind of new. You're going to learn more of this when you get into Algebra 2 and statistics and all of that. But if you're trying to grow, you can't put 0.07 because that is a partial amount that will show shrinking. We want to show that it's increasing 7%. So your number actually has to be larger than 100 because 100% is the same. We need it to increase even more than that. So what you do is you actually take the 1 representing 100% and you add the percent as a decimal, which was 7. And now our number that we're going to use for b is 1.07 because that's going to actually show growth because it's greater than 1. So then you put it all together, and they have written out this equation for you. So it's y, which is our total amount, equals 360, which is our starting billions, times here's our growth rate. It's 1.07 because it's going to grow 7%. Okay, and we know what we're going to plug in for x. We already talked about it. It's the difference between 2005 and where we're at now, supposedly, in that would be 10 years. So we're going to plug in 10 for x, which they've already done down here for you. And they've already calculated it out, thankfully. 1.07 to the 10th power, whatever you get there, times 360. And it looks like we rounded it. You can see this is about $708 billion. So the answer is about $708 billion would be spent at restaurants in the United States in 2015 if that trend continued. Okay, let's try it. We don't actually have to try it yet. We're going to try it on the back. But the you try for today, for this part, is what is just the growth factor? So y-intercept, pattern. Which one is the growth factor? The growth factor is the one that's being raised to the power of x. So the actual growth factor is 4 in this particular equation. Okay, then I'm going to switch it on you. What is the initial amount? So not the growth factor this time, the initial amount. 3 is the growth factor, so our initial amount was the y-intercept. That would be 15. So initial amount, growth factor, growth factor. Okay, let's look at decay. So turn the page and let's check out decay real quick. It says y equals a times b to the x can also be modeling exponential decay as long as, and I'm sure it says this, the value of b will tell you whether it's growing or decaying. So here's the deal. If b is 1, sorry, it has to be larger than 1, then it's growing. If b is between 0 and 1, so think fractions, think half, 1/4, 1/3, 1/8, it doesn't matter. If it's between 0 and 1, it's going to be decaying. So if b is a fraction, it's going to decay. If it's a whole number greater than 1, it's going to be growing. Okay, and if b is decaying, that should have said decay factor, then that means it's going to be a fraction. So, and then this is what the graph looks like of an exponential decay. It kind of looks like our other one, but our other one left to right as you read it starts low and slow and then jumps straight up, like it's going up. This one starts really high, starts like really good. It's almost like the opposite of a good day in the stock market. You have really good stocks and then it plummets. So it just completely decays and it never drops below the x-axis. It just gets very, very, very close the further out you go in the numbers you choose. And again, this would be like 1/2 or something like that. So let's take a look at an example of one modeling with exponential decay. So the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. So for every 1,000 meter increase in altitude, the pressure decreases about 11.5%. So what is the approximate pressure at an altitude of 3,000 meters? So again, you would set it up like we've been doing all of our exponential functions. We're going to let x represent the altitude in thousands. So rather than having to put, what are we looking for, 3,000 in as our little exponent, that would be huge. That wouldn't even fit on our calculator. We're going to measure it in thousands. So instead of 3,000, we're going to call x 3. So in number of thousands. Y is going to be the pressure, and that's what we're trying to find. So we're going to leave y, and we're going to try to solve it. A is the initial. Remember how at the bottom of the U-try, the initial amount was our A term. So our A term is going to be the initial pressure, and it's telling us it's 101 because that's where they started. That's where we've started talking about at 101. And then B is going to be the decay factor. Now, same thing I kind of explained on the back. When you needed this to be over 100% in order to show growth, you need this one to be under 100% in order to show decay. So we want to take this 11.5% and move the decimal back 2 places, and it'd be 0.115, and we need to subtract it from 1 whole. So they've done that for us here. 1 whole minus 0.115 gives us our decay factor, which is 0.885. And that makes sense because when you multiply by a number less than 1, it is going to shrink. And that's what we want because we're decaying here. So they've set it all up. Initial amount 101, 0.885 is our decay factor, and to the x power, and again, I told you we're going to plug in 3 for that because we want to know at 3,000 meters, but we're measuring it in thousands. So we just need to call 3,000 3. So they've solved it all out for you. They took 0.885, they've raised it to the 3rd power, so 0.885 times 0.885 times 0.885 times 101, and they got about 70. So the pressure at an altitude of 3,000 meters is about 70 kilopascals. Okay, we're going to use this same formula here. And now on the U-try, it says, using the information above, what would be the atmospheric pressure at an altitude of 5,000 meters? And again, we're not going to put in 5,000. We're going to measure it in thousands. So we're just going to plug in 5 instead of our 3 here. So let's write out this equation, and we're going to use 5 for our x this time. So we have y equals 101 times 0.885 raised to the 5th power, because we're now asking about 5,000 meters. So good thing I'm going to use my calculator. You have to do order of operations. So this number exponent first. So 0.885 raised to the 5th power equals a big number. And I'm going to leave that on the screen because now I'm going to multiply it times 101. So times 101 equals still a big number, but we're going to say about. So I'm going to round the 8. I'm going to let it bump up 54 to a 55. So I'm going to say it would be about 55, I guess, kilopascals. Kilopascals. Okay. All right. And then a couple more things we're going to look at. What is the decay factor? So remember, this is the initial amount. 17 would be the initial amount. 0.2 is our decay factor. That's what gets raised to the power of x. So our decay factor is 0.2. All right, and then last, I'm making you guys try this whole subtracting from 1 or adding to 1. So it's a population of fish in a lake, and it's decreasing. I hope you guys are reading that word decreasing as knowing that we need this number to be shrinking, decaying annually. So what is the decay factor? We're going to take our 6, make it into a decimal, which is 0.06, and we need to subtract it from 1, because otherwise, if I multiplied by 0.06, it's actually going to get smaller, but not at the right amount, not at the right rate. So I need to subtract it from 1, so 1 minus 0.06, sorry, can't see that, is 0.94. So the decay factor that we would multiply it by would be 0.94 if we were plugging it into our equation.